Hello. Today I want to talk about part 11 of my series on essential theorems for harmonic astrology. And in this part, I'll prove what I call the fundamental theorem of harmonic astrology. So let me share my screen and we'll get started. Takes just a second. Get things going here. I've got to get rid of some panels so I can see what I'm doing. Getting close. Almost there. Okay. And I think we're ready. Essential Theorems for Harmonic Astrology, Part 11, the fundamental theorem of harmonic astrology. The next theorem is what I call the fundamental theorem of harmonic astrology. It establishes a duality between the least common multiple of two harmonics and the greatest common divisor of the corresponding root harmonic angles. I'll prove this theorem first for natural number harmonics, and then extend the result to include all positive rational number harmonics. First, though, I will have to prove a few more lemmas. So we'll start with lemma 2. If x and y are natural numbers, then the greatest common divisor of x and y times the least common multiple of x and y is equal to x times y. And here's the proof. The least common multiple of x and y is the product of all factors that exclusively belong to x times all factors that exclusively belong to y times all factors that are common to both x and y. Furthermore, product of all factors that are common to both x and y is simply the greatest common divisor of x and y. If I now multiply x and y together, then this product contains both all factors that exclusively belong to x and all factors that exclusively belong to y, but it also contains twice all the factors that belong to both x and y. Hence, if I divide out the greatest common divisor of x and y once, then the result will be equal to the least common multiple of x and y. In other words, the least common multiple of x and y is equal to x times y divided by the greatest common divisor of x and y, which implies if you just multiply both sides of this equation by that greatest common divisor, you get greatest common divisor of x and y times the least common multiple of x and y is equal to x times y. Okay, now, lemma 3. If A, B, C, D, and K are natural numbers, then the greatest common divisor of KA over B and KC over D is equal to K over BD times the greatest common divisor of AD and BC. Okay, basically what I'm doing here is I use BD as a common denominator for these two fractions, rewrite each one, and then I can factor out the K over BD, and I'm left with AD and BC inside parentheses here. Okay, the proof. My definition 9, and these definitions you find back in part 2 of this video series. The greatest common divisor of KA over B and KC over D is just equal to the greatest common divisor of these two fractions, where I just rewrote these using BD as a common denominator. And to find the greatest common denominator of these two fractions, you find the greatest common denominator, greatest common divisor of the numerator and divide that by BD. Well, this is 1 over BD times the greatest common divisor of KAD and KBC. Furthermore, since K is a common divisor of both KAD and KBC, it is clear that the greatest common divisor of KAD and KBC, you can take this K out and just rewrite this as K times the greatest common divisor of AD and BC. So therefore, the greatest common divisor of this thing here is equal to 1 over B times greatest common divisor of KAD and KBC. And this in turn is going to be equal to K over BD times the greatest common divisor of AD and BC. You can just take out this K, and it winds up in the numerator here over BD. Okay, and that's the end of that proof. And this brings us to the fundamental theorem of harmonic astrology. So suppose that M and N are natural numbers greater than 1. That is for convenience. If you use 1 as a natural number here, that often creates a special case, since for the 1 harmonic, you get 360 degrees divided by 1 is 360 degrees, and then you have to reduce that modulo 360 to get the root harmonic angle of 0 degrees. But if M and N are greater than 1, then when you divide 360 degrees by M or N, you automatically get the root harmonic angles. So let's suppose that M and N are natural numbers greater than 1, and that theta sub M and theta sub N are the corresponding M and N root harmonic angles, which we get by just dividing 360 degrees in turn by M and N. Also, denote the least common multiple of M and N by LCM M comma N, and the greatest common divisor of theta sub M and theta sub N by GCD of theta sub M comma theta sub N. Then the greatest common divisor of theta sub M comma theta sub N will be equal to 360 degrees divided by the least common multiple of these two harmonics. This divided by this gives you the greatest common divisor of these two root harmonic angles. So, using limit 2 and limit 3 and definition 9, I have that the greatest common divisor of M and N times the least common multiple of M and N is equal to M times N. And then you can just do a little algebra with this equation to rewrite it as 1 over the least common multiple of M and N is equal to the greatest common divisor of M and N divided by M times N. Multiply both sides of this equation by 360 degrees, and you get this. And then this is going to be equal to 360 degrees times the greatest common divisor of these two fractions. I just moved M times N back into this expression as a denominator. I'm kind of doing some definition 9 or some of these things in reverse to make the expression a little more complicated, perhaps. But once I get this, I can reduce these fractions, and they reduce to 1 over N and 1 over M. And then I can move the 360 degrees back into this expression. I get 300 greatest common divisor of 360 degrees over N, comma, 360 degrees over M. But these guys, in turn, are going to be the root N and M harmonic angles, respectively. So this comes out equal to greatest common divisor of these two root harmonic angles. And that, let's see, that is equal to 360 degrees divided by the least common multiple of these two harmonics. And that completes the proof. Okay, I now give a corollary to Theorem 14 that extends the result to all positive rational numbers. So let's suppose A, B, C, and D are natural numbers, such that A over B and C over D are positive rational numbers greater than 1. Remember that positive rational numbers that are less than 1, there's always going to be a corresponding harmonic greater than 1, which gives the same root harmonic angle. So if I can prove this for positive rational numbers greater than 1, I've got it for those less than 1 also. Okay, so let's suppose that. And let's let 360 degrees divided by A over B and 360 degrees divided by C over D be the corresponding root harmonic angles. Uh, since these fractions are greater than 1, these ratios are going to be less than 360 degrees, so I don't need to do a reduction modulo 360 degrees. Okay, given all that, then the greatest common divisor of these two root harmonic angles will be equal to 360 degrees divided by the least common multiple of these two rational numbers. And to prove this, I will use definitions 7 and 9, again from part 2 of this video series, and the results from limit 2 and limit 3. In particular, that if x and y are natural numbers, then the greatest common divisor of x and y times least common multiple of x and y is equal to x times y, which implies that the greatest common divisor of x and y is equal to xy divided by the least common multiple of x and y. And I've left off a parentheses here, and I left off let's see, there should be a comma here, but I'll go ahead and fix that later. So this should be LCM of x comma y, parentheses close. Sorry about that typo. So on the one hand, we have that 360 degrees divided by the least common multiple of these two fractions. Well, you could write these fractions with BD as a common denominator. And then by definition, this is going to be equal to the least common multiple of those numerators divided by that common denominator. You can simplify this complex fraction by flipping the denominator that puts b times d on top. Okay? So we have that on the one hand, but on the other hand, the greatest common divisor of these two root harmonic angles is going to be equal to 360 degrees. You can pull that out in front, and then you can flip these fractions in the denominator and write that as the greatest common divisor of b over a and d over c. And now you could rewrite these two fractions with a times c as a common denominator, and then that is going to be equal to 360 degrees times the greatest common divisor of the numerators divided by AC. I have some schmutz here. I've got to get rid of that also. So again, I got a couple of things to clean up in this proof. Sorry about that. But this will be equal to 360 degrees. And now what do we do? I take the greatest common divisor of, let's see, BC and AD. I can replace that. I use this result here. I replace it with the product BC AD divided by the least common multiple of BC and AD. And that's all over AC. Okay. Well, let's see. I can cancel out the AC here with the A and the C in this numerator. Rewrite that as this as 360 degrees times B times D over the least common multiple of BC and AD. And if I take the B times D down below, I can rewrite this as 360 degrees over least common multiple of BC and AD. This least common multiple divided by B times D. Okay, and now I can move this divisor BD into this expression. I can divide each of these terms by BD, which is what I do here. And then if I reduce these fractions, I get 360 degrees over the least common multiple of C over D and A over B. And then I'm just going to switch these two. If I do least common multiple of this and this, that's the same as least common multiple of the second one and the first one. So this is 360 degrees over least common multiple of A over B and C over D. We got that this is equal to the greatest common divisor of these two root harmonic angles, that's exactly what we want to prove. And so we're done. Let me stop sharing my screen here. Okay, and I'm back. And that's it with a couple of minor typos that I will fix as soon as I end this video. Uh, but I hope you enjoyed that, and I hope my walkthrough of all of these proofs for theorems about harmonic astrology has makes those proofs easier to understand if you go back and look at them in written form. And for now, I'll just say so long and be well.